Hello everyone, welcome to the class. So basically in this class, we will learn about dynamic programming. So we will cover the basics of dynamic programming, like we will learn like what exactly is dynamic programming, why it is necessary, and how it improves, you can say, the time complexity, how it reduces the actual time taken in some basic recursion problem. So we will see that. So basically in a like in a high level view, you will get an idea like why we need dynamic programming and what is the use of it. Okay, so dynamic programming, ideally you can say, is like a very common term which is given to it, is known as it basically enhances the recursion. Okay, it enhances any basic recursion. Okay, and how it enhances, basically it reduces the time taken by the recursive problem. Okay, by adding some techniques in it. Okay, so this is basically dynamic programming. Okay, so dynamic programming, like you can say how it enhances. Now the question comes. So basically, tries to it tries to memorize the states. Okay, of different recursion calls. Okay, of different recursion calls. Okay, and then reuse that state. Okay, then reuse that state. So this is called basically, you can say, dynamic programming, like how it enhances the recursion. Okay, so let's see a very simple example through which I will tell, okay, how this can be a problem with the recursion, whereas if you solve it using dynamic programming, it can save you a lot of time. Okay, so let's see that first of all. So let's take an example of Fibonacci problem only, which is a very, you can say, standard problem we use to describe dynamic programming. Okay, so if I talk about, you can say, Fibonacci. Okay, everyone knows that the Fibonacci recurrence relation formula is, let's say if you want to calculate f of n, you need to get it from f of n minus 1 plus f of n minus 2. Okay, you need to get this only then you would be able to, you can say, like this is a recurrence relation basically, ultimately. Okay, and if I draw a recursive tree, okay, of Fibonacci. Okay, so let's say, let me draw a recursive tree. So if you see, this is, let's say I want to calculate Fibonacci of, let's say 5. Let's say I want to calculate Fibonacci of 5. If I want to calculate Fibonacci of 5, what I need to calculate for that? I need to calculate Fibonacci of 4. I need to calculate Fibonacci of 3. For 4, I need to calculate again Fibonacci of 3. And for 4, I need to calculate Fibonacci of 2. Similarly, for this, I need to do this, Fibonacci of 2 and Fibonacci of 1. Okay. Similarly, again for Fibonacci of 3, I need to calculate Fibonacci of 2 and Fibonacci of 1. Similarly, for Fibonacci of 2, I need to calculate Fibonacci of 1, okay, and Fibonacci of 0. Similarly here, so Fibonacci of 1, you know that if I ask you about Fibonacci of 0, you will tell me 0. If I ask you Fibonacci of 1, you will tell me 1, right? So this will be the base condition ultimately. Similarly, if I a little bit go down, you will see that, okay, Fibonacci of 2, Fibonacci of 1. So yeah, this will be again two recursion call. This will be the base condition, this will be the base condition, and this will be the base condition. Okay, so now guys, please observe. So what is this? This is how, let's say if you have written the recursive solution for the Fibonacci, you will see that like this is the tree which Fibonacci will form while, you can say, while running basically. Okay, and you can see that there are a lot of overlapping states. Overlapping state means, here you can see that Fibonacci of 3 is being calculated, whereas over here also it is being calculated, right? So at two different places it is being calculated. Similarly, if I talk about Fibonacci of 2, it is being calculated here, it is being calculated here, it is being calculated here. Okay, now the thing is that here you can see that Fibonacci of 3 is calculating twice, Fibonacci of 2 is getting calculated twice, where Fibonacci of 1 and 0 are the base conditions, so that will just be a simple return. Okay, but let's consider if this was Fibonacci of, right now since I have only added Fibonacci of 5, let's consider like if it was Fibonacci of 8, Fibonacci of 10, right? Over there, how many overlapping these states would be, right? there would be many, you can say, states which will be calculating again and again, right? So just think, like if we have calculated Fibonacci of 3 over here, do we need to calculate again Fibonacci of 3 here, or we can just calculate it here, save it, save the result somewhere, and then reuse it once it comes back here? Can we do that? Yes, we can do that. And that is what dynamic programming helps us to achieve. Okay, because I don't want to calculate this Fibonacci of 3 again and again, right? If one time I have calculated, let's just store it, so that in the next time I'm able to, you can say, I'm able to, you can say, like just reuse that logic, just reuse that answer for me. Okay, and this is how dynamic programming helps. Okay, so ideally you can say that this is what dynamic programming does. Okay, whereas dynamic programming has actually two types of solutions, like you already have, most of you have heard, like one is your bottom up, okay, and other is your top down. Okay, so in top down solution, it's your recursion, basic recursion plus memoization. We say as memoization. Okay, memoization or memorization, whatever you want to say. This is the way. In bottom up, it's about filling a table. Okay, so basically the thing is that bottom up is little bit advanced solution for top down, although it is doing the same thing. Okay, it is even memorizing the results and then calculating the further states. Okay, in the bottom up also, we are not calculating a state again and again. In that also, a state is being calculated once, although you can say the things you do in bottom up and top down are pretty different. Okay, because in bottom up we don't use recursion, we just use a technique to fill a table. Okay, and that can be using either one for loop, two for loop, three for loops, depending upon the solution. Okay, so this is also known as tabular method. Okay, why tabular method? Because we fill a table here. Okay, and guys, the most intuitive solution, like once you are learning dynamic programming, is the top down. Okay, bottom up comes via practice. Okay, once you have achieved a good amount of like you have done a good amount of practice in top down, and like bottom up is not a very big game. It's just, you can say, a conversion of a top down solution to bottom up. And in interview, if you are telling about the top down solution, that's absolutely fine, no problem in that, that's easily accepted. Okay, so and this is even more intuitive. Okay, this will give you more intuitive, and you need to know the recursion. And once you, because if you are good in recursion, this top down is a cakewalk for all of you. Okay, and because this adding a memorization step is very simple, it's just, you can say, adding some just do the memorizing of different states and reusing that state if that state is being called again. Okay, so these are some two basic bottom up and top down, like these are two type of solutions we write for dynamic programming. In this video, I will just discuss more on top down for the Fibonacci. Okay, now let's just do one thing. Let's write the Fibonacci code. Okay. I will apply the, you can say, first of all, recursion. Okay. Then I will apply the top-down approach, like adding the memorization in it. And we will compare the time complexities, like how it is reducing the time. And we will see how significantly it reduces the time. Okay. So I'll now share the other tab. Okay. So I hope you can see my tab here. Okay, the coding tab. So let's write the basic Fibonacci problem. Okay, so I'm writing in Python for now. Okay, so let's say this is the Fibonacci function, and I need to find the nth, basically Fibonacci of n, basically. Okay, you all know that. Okay, Fibo of n is Fibo of n minus 1 plus Fibo of n minus 2. That's it. Okay, and obviously there is a base condition in every recursion problem. There is a base condition where it tells, okay, that you need to stop here. After that, you don't need to go to further recursion calls. Okay, so just check if n is less than equals to 1. You know that here you just need to return n, nothing you need to do. Okay, otherwise what you need to do, Fibo of n minus 1 plus Fibo of n minus 2. Okay, And now let's just do one thing. Let's import a module called time in Python. And similar, guys, you can do in C++ also. That's a very simple thing. Okay. So let's calculate the time, how much the execution is taking. Okay. So I'll just write here. Okay. So this is the start time. And let me call the function in between so that it can calculate the Fibonacci of, let's assume I'm writing 30, Fibonacci of 30. Okay. And let me just print the, let me just get the end time. And then what I will do, I will just print what end time minus start time. Okay. So what it will give me, it will give me, now see guys, when I'm executing start time before the function, and when I'm executing the end time before, after the function is called and printed, it will be called, and this will calculate the difference, like the how much the time is taken by this particular function for Fibonacci of 30. So let's run this code. Okay. So I'm running this code, and you can see that Fibonacci of 30 is giving you this is the value of Fibonacci 30, and this is the time in seconds which it is taking. I guess it is 0.6 second, which is, you can say, 666 millisecond. Okay, and let me just increase this 30 to, let's say, what time does it take now? Okay, so now you can see the time taken is 2.455 seconds. Okay, which is obviously pretty huge. Okay, now, how can I reduce that? I told you that we will do the memoization. Okay, and how can I do the memoization? You can use a map data structure. You can use an array data structure. So basically, in memoization, what we do, let's say, first of all, let's assume there is a map. There is a map. Okay, there's a map, and how you will do the memorization. Okay, so basically you can say that, let's say, you want to calculate Fibonacci of 4. Okay, so before going on to the recursion, you will just check whether this 4 exists in the map or not. Okay, whether this 4 exists in the map or not. If it does not exist, go into the recursion call and calculate the Fibonacci of 4. And before returning, just save that value in the map. So let's say Fibo of 4 is something, let's say X. Like after calculation, it came out to be X, let's say. So it will be stored in the map before returning, guys, before returning. And let's suppose in some other states, in some other function call, I got that, okay, I again want to calculate Fibonacci of 4. Now, when I will now look into my map, it will tell me, yes, there is a 4 state, and you can reuse that state. Don't need to go into the further recursion calls. Okay, so I'll write the code. I'll write the code for this. Maybe this will make you clear. So in Python, what we do, like, I guess we have dictionary. Okay, we have dictionary we use as a map. Okay, so I'm just naming the variable as memo, and obviously, guys, like, I'm declaring it globally, but yeah, you can pass it in the function and just as a reference and reuse that. Okay, just for easy to make it easy, I'm just using globally right now. Okay, as I told you, you will just check. Okay, if n is in memo. Okay, so basically it is checking, okay, if n is present in the map or not. If it is present, so basically is in will check, okay, if it is present in memo or not. So it will just return memo of n. So it means that if it was present, it will return that value. Otherwise, it will go into the recursion call. And I told you that you have to store the value before returning it. You have to store the value before. Sorry, I wrote meme. Sorry for that. So it is return memo and n. So what I did, I am storing the value before returning it. Okay. So I hope you got the idea, and let me just run it. So I hope it runs. I guess there's some syntax error. Oh, sorry. I guess this is will not come. If n in memo, sorry for that. If n in memo. So guys, now please clearly see this, that if you see, the value is similar what was calculated before, but you can see the time, how much time is reduced. So you can say that it's earlier it was 2.455 seconds. Now now it is 5.316 into 10 to the power, you can say minus 5. It is 10 to the power minus 5, and it is very less. If you can see, it is very, very less. Okay. And like, that's how you can see that how much time it reduced, just only applying this memoization. So if someone tells, okay, this is your top down solution of dynamic programming for the Fibonacci. Okay, for the Fibonacci, and this is the top down solution for it. Okay, and you can easily see that, guys, like how it reduced the time complexity from 2.45 second to this, like 5.316 into 10 to the power minus 5. So much less, so much less. That's how, guys, we you can say, that's why basically we use dynamic programming. Okay, and ultimately in all the dynamic programming solutions that you will see, okay, you will see that they can be easily solved with this top down approach. Okay, and obviously, guys, I told you that bottom up comes with the practice. Okay, and if you ask me about, okay, how the bottom up solution you can write, so that is, you can say, like just a simple for loop technique, and you have to just fill that array, right? I hope you already know that solution. Like, so basically, if this is an array, let's say this is of n, where the 0th term is 0 and this is 1. So the second term you will get, the by the addition of this, you will fill this cell, it will become 1, and for this you will do the addition of this cell and this will become 2, and similarly go on. So this is your bottom up approach, guys. Okay, and if you ask me, like, which is more time efficient, bottom up or top down, obviously bottom up is more efficient. Why? Because there are few recursion calls. Because in the top down approach, what you are doing is, you are checking in the cache, right, whether it exists or not, and then you are returning that. So that is adding some extra time, you can say. Okay, but you can say, both it will not be very significant. It will not be very significant, like what you saw right now, like from 2.45 second it reduced to such like 10 to the minus 5 range. Okay, it will not be that significant. It will be just few milliseconds, you can say. Okay, but yeah, like top down solution is easily accepted in the interviews and even in the coding round, so don't need to worry about that. Okay, so this is basically, guys, like obviously, like, I wanted to give you an idea like why dynamic programming we use, and how it reduces the time. Okay, and only one thing I just want to tell you before that, like like basically, if you ask me about, okay, what was the time complexity of recursion of Fibonacci and why it was taking so much of time. So let's see that. Okay, let's calculate the time complexity. Okay, so you know that if you want to calculate the Fibonacci of n, so it will take t n minus 1 plus t of n minus 2. So basically it tells, okay, time taken to calculate the nth term is equals to time taken to get the n minus 1 plus time taken by n minus 2 term. Okay, so this is like, obviously, like this is the reconciliation for the time, also. Okay, and let's suppose if n is very large, so you can say that n minus 1 is comparable to n minus 2. Obviously there will be some constant also, there will be some constant time taken also. So n minus 1 will be comparable to n minus 2, and hence you can write something like this: n minus 1 plus t of n minus 1 plus c, and this will become 2t n minus 1 plus c, right? And let's write it, guys, for the further. Let's say you want to calculate t of n minus 1, so you can write 2 of t n minus 2 plus c. T of n minus 2 will give you 2 into t of n minus 3 plus c. Similarly, guys, go on, and at the last you will get t of 1 into 2t of 0 plus c. Okay, now, guys, see what you want to ultimately calculate. You need to calculate the time taken by the nth term, right? So you need to vanish out all these extra n minus 2, n minus 3, some intermediate time complexities. Okay, so how you can vanish that? So if it is multiplied by 2 on the right hand side, you need to multiply 2 on the here also, right? So if you multiply 2, like this will become 4, and this will also become 2. Now this t of n minus 2 is 4, so obviously this will become 4, this will become 8, and this will become 8. Similarly, like obviously when you will go on, like if you see, like if this is n minus 1, this is 2 to the power 1. If this is n minus 2, this is 2 to the power 2, and this is what? This is actually n minus 1. So this will be 2 to the power n minus 1 2 to the power n minus 1 into 2 will become 2 to the power n, and this will become 2 to the power n minus 1. Now, if you add all those, you can say this will cancel out this will cancel out this will cancel out somewhere this, and this will cancel out somewhere here, right? And ultimately, you will be left with these logics, guys. Please clearly see, t of n is giving you what? You can say it will give you, first of all, c plus 2c. I guess my bad, this was 8, this was 4c, right? Because we multiplied by 4. This was 4c, we will get somehow 8c, plus so on till 2 to the power n minus 1c, plus we'll get 2 to the power n t of 0. And guys, see, this is a constant sum, so don't need to worry. So you can say it will become t of n, let it be, you can say 1, okay, or k, whatever we want to keep, okay, some constant, okay, let's say it is k, okay, plus let's take c common, guys. C common, if you take c common from here, okay, let's take c common, it will become 1 plus 2 plus 4 plus 8 plus 2 to the power n minus 1. Now, guys, see, this is a GP. This is a GP series. If this is a GP series, you know, like the sum of GP is what? It is, I guess, a into r to the power n minus 1 upon r minus 1 for a finite GP series, right? So this will become like this. A here is 1, r is 2, total there are n terms, so it will become something like this, right? Now what will happen? It will become something like 2 to the power n k plus c 2 to the power n minus 1. Okay. And obviously, guys, if n was very large, like, you can just ignore this 1, because this 1 doesn't make sense, because if n is very large, so you can just write 2 to the power n c, and ultimately you will get this 2 to the power n k plus c, which is a new constant, and you can just write 2 to the power n, let's say p, which is a new constant, and hence t to the power n equals to 2 to the power n into p. And you can see here, guys, very clearly, that, see how much the time is taking. It is taking exponential time, guys, exponential time. Like, it is proportional to 2 to the power n. The more the n is, it will shoot up, and you know the exponential graph, like how it goes, right? So if the n will increase, it will increase drastically, right? So that's why this basic recursion problem cannot help you here. Okay, you have to apply memoization, then only it will be reduced. And in the memoization, it will be a sort of a linear time complexity. Why linear time complexity? Because, see, let's say you want to calculate Fibonacci of 5. So for Fibonacci of 5, you need to have the states of 5, not 5, because 5 you are already calculating. You need to have the states of 4, 3, 2, 1, 0. And in the top down, also you were calculating already these states only once, due to caching. You were only calculating these states once, and after that you are reusing. So if you're calculating all these states once, ultimately, what is the time complexity? It will be linear, sort of. Okay. Although in top down, it will take some extra time in checking, okay, if that exists in the cache or not. But if you see the bottom up, like in the Fibonacci, it was totally a it was totally a linear, right? Where you were filling this table, right? Where you're filling this array, right? If this was 0, 1, this was 1, this was 2, this was 3, and so on. So it was linear. And obviously, guys, linear is far better than the exponential time complexity. That's why you were getting like so much time difference, right? If you saw here, there was so much time difference in the dynamic programming problem solution, and in the basic recursion, right? So this is the idea, guys, behind the like why we use dynamic programming. Obviously, I cannot explain all the problems in this video, so like, I hope you liked what I taught. And guys, this is like the basics of DP. Obviously, there is more to DP. Obviously, we will learn when we will be going through the course. So I hope you enjoyed the class. So thank you very much, guys, and that's it from my side.